Hello again. Welcome back. Here we are in the sixth week of the semester, and we're just continuing along with our exploration of the various inputs that are used in automotive computer systems. We've talked about so far thermistors, potentiometers, switches. So we're going to talk a little bit about data streams, but not very much now. We'll talk about those later and then continue on with AC signal generators, DC signal generators. We'll talk about air-fuel ratio sensors. Let me, in fact, shut me off here, and we should be sharing my screen. Here we go. All right, so let's click on one of our courses here. And we've got our slides. This is what we've been working in. So let me click on that, open it up. All right. So where we were at, let me get down here to the list of inputs. We were talking about these inputs, right? And so far, we had done thermistors, potentiometers, switches, which was last week's topic. Now we'll do data streams, AC generators, DC generators, pressure sensors, and other sensors. We'll see how far we get today. Let me scroll ahead now to where we were. So data streams. One of the things that is different about cars nowadays than years ago is that there are various computers in these cars, and they can talk to each other. They can share information. So one example would be vehicle speed. Rather than have one sensor feeding the dashboard for the speedometer and a different sensor feeding the powertrain control module for road speed, like for transmission shifting, for example, instead of having multiple sensors, one sensor can be shared over the network. So maybe the vehicle speed sensor feeds into the PCM, and then the PCM shares that vehicle speed information with the instrument panel cluster, which can then display it as either a digital or a needle on the speedometer. Just one example. So data streams, really, these are electrical circuits. So not to get too crazy, there's not anything magic going over these wires. They are electrical impulses, and I have down here 1 and 0, which we oversimplified by saying that's basically on and off, but that's not entirely the case necessarily. It depends on the computer systems that are trying to talk exactly what equals a 1 and what equals a 0. More on that in a minute. So there's going to be a single wire or a pair of wires connecting the computers together. We'll talk about the physical layer when we talk about outputs, but just wiring, nothing fancy. And on that wire will be a voltage level. It may be, above a certain voltage level is considered high, and below a certain voltage level is considered low. So let's just, to simplify things, let's just use 12 volts, although they don't. But just picture that if there's 12 volts on the wire, that circuit is considered to be high. And if there's 0 volts on the wire, that circuit is considered to be low. In real life, those thresholds might be different. It might be, anything over 3.5 volts is considered high, for example. I don't care because I can't really see this in real time. I can't really put a scope on there. I can put a voltmeter. I can get kind of averages and things like that, but it doesn't really tell me anything. So just suffice it to say, these are electrical signals, and the voltage level on the wire goes up and down. All right. So between what we would call high and what we would call low. And we don't care what equals a high or what equals a low so much. And like I said earlier, it's similar to Morse code. In other words, there are series or sequences of 1s and 0s that identify, what information is being sent over the network. So patterns of bits. So every 1 and 0 is a bit, and patterns of them can equal letters, numbers, whatever. So maybe serial or parallel. So let's talk about that for a minute, just really quickly. And I think I'll talk more about this when we talk about the wiring and stuff like that. But just very briefly. So here's computer 1. Here's computer 2. Right? Let's say, since a byte, one piece of information is 8 bits, let me just string 8 wires between these. So there's 1, whoops, 2, 3, 4, 5, 6, whoops, 7, and 8. 8 wires. And so if I had, some data here, how many is that? 1, 2, 3, 4, 5, 6, 7, 8. All right, so 1 byte of data, and I wanted to transmit it, from this computer over to this computer. In one shot, right? All of these right here can be sent across and land over here in one pulse, right? 1 bit on each wire. So very, very fast. The big downside here is if we're putting that many wires in the car, the wiring harnesses would be ridiculous. So we do have high speed, but we have complexity of wiring, right? So let me get rid of all this a minute and talk about another way of doing it, right? And so we could have computer A here, computer B here, and then just run a pair of wires, and typically they're going to be twisted. So let me see if I can twist them, right? So twisted pair of wires between the two. And so that's, let's say a power and a ground. And if we have that same, now I don't remember what the actual number I used was, 0, 1, whoops, 1, 1, 0, maybe 1, 1, 1, 0, I don't remember. So if I have that and I want to transmit it across the network over here, right, I'm sending it 1 bit at a time in a series. So we call that serial communication. And the obvious downside there is that instead of 1 single pulse, clock pulse, it's going to take 8 to send this byte of data across that network. And the obvious upside is the wiring is way more simplified, right? We just have 2 wires. So it's a trade-off. And the chips and the wiring, so far, for the data rates, the speeds we need so far, serial is more than adequate, right? And we see this on all kinds of computers, right? USB stands for Universal Serial Bus. That's the whole idea. If you look, there's basically, power or ground, and then there's the actual data is transferred on 2 wires, and it's transferred in series. So that's a quick and dirty explanation of serial or parallel, and the the trade-offs between the two. I don't see anything. We used to have parallel printers years ago. They had a cable, a really thick cable between the computer and the printer with a lot of pins. And now what do you have? Usually a USB cable, right? There's 4 wires in there, and it's plenty fast enough for what we need. All right. We talked about this in an earlier slide, these American Standard Characters for Information Interchange. And this is just to give you an example. Don't worry about memorizing these, but every letter, digit, punctuation mark, can be broken down into an 8-bit, really 7 is enough, pattern, so that when it's transferred across the network, the computer transmitting it and the computer receiving it see the same thing. As long as they have the same idea of what equals a, let's say, uppercase K, or what equals, the number 8, as long as they both agree, they're both talking the same language, the same protocol, then they can talk to each other. So there are standards. A clock keeps things synchronized. You may realize some computers operate at a higher clock speed. Some networks operate at a higher speed. We'll talk about that later. The old-fashioned car networks were very slow. The modern CAN bus are very fast. As long as both computers speak the same language, they'll communicate. So here is J1850, and if you don't recognize that terminology, the Society of Automotive Engineers, I guess now called SAE International, comes out with these standards. Standard J1850, is one of their standards for data communication in automobiles between different modules or computers. And the VPW stands for variable pulse width. And if you notice, there are two ways a zero can be represented down here. A zero can be low for a short period of time, or it can also be high for a longer period of time. By the same token, a 1 can be a short high pulse or a long low pulse. So this is how the computers differentiate between zeros and ones as they're transmitting things down the network. So low for 64 microseconds. This is in this one particular protocol. This is not necessarily the same for CAN bus. But this J1850 variable pulse width, low for 64 microseconds is a 0, or high for 128 microseconds is also a 0. A 1 could be low for 128 or high for 64. Do you need to know this in order to actually diagnose and repair cars? No, you do not. This is just background information. You plug a scan tool in, assuming it speaks the language that the car speaks, it's going to be able to interpret these things for you and display things on the screen that are useful to you. All right, so that'll do it. We'll talk about the wiring and the diagnostics for networks and the different kinds of networks. There have been a lot over the years, but we've kind of settled now in most vehicles on CAN, controller area network. That's been out since 1984, Robert Bosch, but it really didn't make it into wide acceptance sometime into the 90s, and it's kind of a standard now. Most vehicles actually have multiple networks. They may have medium speed CAN, high speed CAN, single wire, 2-wire. There may be LIN networks. It's just a lot of different protocols in use. As long as your scan tool knows how to speak those protocols, it can get you the data you need. So let's move on. AC generators. So the AC, of course, stands for alternating current. I don't want to reteach the electrical class here. You should be familiar with electromagnetic induction. And this is the concept that when a magnetic field and a wire move in relation to each other, there's a current generated in the wire. It doesn't matter whether the magnetic field is in motion or the wire is in motion. As long as relative to each other they're moving, there will be current generated in the wire. And the amount of current is based on a lot of different things. If the wire is coiled around that magnetic field, that will increase the output. If it's coiled around, in the vicinity of ferrous material, iron, steel, that will concentrate the magnetic field. That can increase the output. Another big thing is the speed at which that magnetic field or that wire are moving. So because these things are variable based on speed, they can be used as speed sensors. They generate a small alternating current voltage. I'm going to talk in a little bit how the voltage is not necessarily the most important thing, but they are used to measure speed. A higher voltage and/or frequency means a faster speed. So I just finished saying that, a lot of different things affect the voltage out of an AC generator. One of those is how close the magnetic field is to the wire. And a lot of sensors, I'll look at one in a minute, there's possibly a little bit of variance in that. So that could change the voltage coming out and it could make the sensor inaccurate. But the frequency is really just going to be based on how fast teeth are passing by the sensor. And it won't matter if there's a bigger or smaller gap in the sensor. It won't change the frequency. It will affect the voltage. So let's see, examples: crankshaft and wheel speed sensors, cam sensors possibly. And then the computer takes this AC, converts it and to DC, and then turns that into digital. So crossing zero voltage level can indicate position. So let me say try to explain what I mean by that. Let me just draw here, right? So here is a line which indicates 0 volts. Let's say 0 volts. Up here, let me put, I'll put 5 volts. Doesn't matter. Down here, I'll put, negative 5 volts. And the output from this sensor, oh, for heaven's sake, my apologies. We'll do that again. 5 volts here, 0 volts here, and negative 5 volts here. And our line, 0 volts. And the output from this sensor, as the teeth are rotating, and let's say this gap, as it's moving closer to the sensor, our voltage is going to go in one direction, and as it's moving away, the voltage is going to go in a different direction. So we're going to see a voltage level that looks like this, going up, then going down, then going up, then going down, then going up. And the important thing here is if the computer just counted any one of these points, right? Count every time it hits the high point, there, there. Count every time it hits the low point, there, doesn't matter. Or count every time it crosses 0, right? It can see how rapidly or how frequently these gaps are passing by the sensor and turn that into a rotational speed. So the actual voltage level may not be quite that important, because if I move this sensor here a little bit further away from this wheel, the voltage level would drop across the board. But what would not change is how often, right, we cross this 0 point. That would happen every time a tooth comes around. So if we were just counting how rapidly, the frequency that those are coming in, we can turn that into a speed. Notice there are 2 pins on this sensor, right? A AC generator is really simply, move this out of the way, a wire that starts here, wraps around a magnet, probably thousands of times, right? And then comes back out here. So inside this coil of wire is a magnet. And every time one of these gaps passes that magnet, it causes the magnetic field around that magnet to wobble. And when it wobbles across that wire, causing a little bit of a spike out of it. And that's all we need to count, just how frequently that magnetic field wobbles based on the rotation of this wheel. This is an example of a crank sensor we're looking at here. This whole thing here is a crank sensor. And the interesting thing, this would be out of a V6, I assume. Every 60 degrees, we have another gap. So as this crankshaft is turning, the computer is going to be updated every 60 degrees on where it is. But in order to know what the number one cylinder is, right? So this wheel is cast into the crankshaft here. When the number one cylinder comes up, top dead center compression stroke, this double notch is going to hit the sensor. And that way the computer knows, oh, that was the number one cylinder, that, you know, and then it can just kind of count from there. 60 degrees later is going to be the next one in order. And then another 60 degrees will be the next one in the firing order. Once it knows where number one is, it can just figure it out from there. So most of these sensors have some sort of method of identifying which cylinder, if this is a crankshaft position sensor. If it's a wheel speed sensor, if it's a vehicle speed sensor, an input shaft speed sensor, an output shaft speed sensor, any of those sorts of things, it doesn't care about the actual position. All it's looking at is speed, right? Rotational speed. None of this should be brand new to you. If you took engine performance, if you took electrical, you should be familiar with electromagnetic induction. And particularly engine performance, you should have talked about things like crankshaft sensors. So this should just be a review, basically. Just realize you'll find the same type of sensor all over the car. Anytime you're looking at rotational speed, it might be a AC signal generator type sensor like this. The key to identify this is, one, it will have two wires, where the other method, Hall effect, has three wires. This has just two wires. And if you're trying to measure the output from this thing, you are going to need your voltmeter set on alternating current. So it generates its own AC voltage. You do not supply any kind of reference voltage to this sensor. It generates its own. Here's just a quick, representation of the difference between an analog signal and a digital signal. And we just said that AC signal generator, that's putting out analog AC. So here's the key between analog and digital. All right. Analog, this voltage level is changing over a period of time, right? So our line does not go straight up, right? As the voltage is increasing, it's taking some time here. It's taking even longer. So time is this way. So it's down low for a while, but it slowly ramps up, reaches a peak over a period of time, slowly ramps down. The digital one, on the other hand, it's here at zero or low, and then bam, it's turned on like a switch. So a digital signal is more like a switch. An analog signal is more like a dimmer switch, where you can take and turn your lights up, turn them down, or a volume knob where you can turn it up, turn it down. And there are all kinds of interim levels in between on and off. Digital, no time passes. Here you're off, bam, here you're on with no time passing. It's instantaneous. And it stays on for a while and then off instantaneously. It's like flipping a switch. So what type of a signal does an AC generator provide? I'm going to leave that blank because, we will eventually have a test on this stuff actually coming up pretty soon. I'll let you know. And what are two examples of this type of sensor? So where might you find this type of sensor on the car? There's a lot of examples. I'm just looking for a couple. So we'll move on. DC generators. Now notice I'm using the term generator. So what does that tell you? That tells you that the sensor itself is creating the electricity. To my knowledge, there's only one used in cars that does that creates direct current, and that is an oxygen sensor, an exhaust gas oxygen sensor. As far as AC generators, like I told you, they're all over the car. But DC generators, I'm really talking about an O2 sensor. And as of late, and when I say as of late, I'm talking about quite a few years now, these are sort of being phased out in some cases in favor of a more accurate air-fuel ratio sensor. So you may find that cars have air-fuel ratio sensors feeding information back to the computer for fuel control, and then they might have a conventional oxygen sensor like we're about to talk about, feeding information back for catalyst efficiency. That's getting to be a real common setup, right? An air-fuel ratio sensor in front of the cat and an old-fashioned oxygen sensor behind the cat. So if you've ever explored how a battery works, whether it's a car battery, a AA battery, a 9-volt battery, what you find is it operates on a chemical reaction where there's a reaction between some sort of metal and there's an electrolyte. And because the metals are dissimilar, then electrons are displaced to the point where they build up on one side and they are lacking on the other, and you wind up having a voltage. And so it's a chemical reaction using materials and creating a voltage, right? And now a 9-volt battery is obviously 9 volts. A double or AAA is 1.5 volts. An oxygen sensor generates maybe up to about 1 volt. So if you're measuring the voltage off of one of these things, the most you're likely to see is about 1 volt. So it's a 1 volt battery, but it doesn't always put out 1 volt. That's the weird thing about this. If I hand you a AA battery, as long as it's brand new, right, it's going to put out 1.5 volts. If I hand you an oxygen sensor, it could put out, depending on the environment it's living in at the moment, anywhere from 0 volts to 1 volt, and all of them are valid. All of them are good voltages. It's the voltage that the computer is using to understand what's going on in the engine. So I've already said all that. So we have exhaust gas contacting an inner electrode, air from outside the vehicle contacting an outer electrode. If the oxygen content of the exhaust is the same as the oxygen content of the outside air, the voltage is going to be 0. Well, when's that going to happen? Obviously, if the engine is off, what's in the exhaust is going to be the same as what's outside the exhaust, right? But as soon as the engine is running, there should be some sort of a difference in the oxygen content. And that's what this sensor is really measuring. So here's a picture, and it's a little goofy, so let me just go through and try to explain. This is an old picture. There's only one wire, which never happens anymore, right? So this one wire, and it's grounded by the fact that it's screwed in here. These are threads that it's screwed into the exhaust. Typically now, there'd be a separate ground wire going straight back to the computer. Because the problem with grounding it, here, by the way it's threaded in, is the exhaust is rusty. Where the exhaust manifold attaches, or the exhaust pipe attaches to the manifold, there could be rust. Where the manifold attaches to the cylinder head, there could be corrosion, rust. Between the engine and the body, there could be some corrosion. Between the body and the computer, there could be some corrosion. So essentially, there are all these opportunities for voltage drop to happen every time this encounters any kind of corrosion on the way back to the computer. Now, in a headlight circuit, if you drop a half a volt because of a little bit of corrosion or something like that, the light might be a little bit dimmer, but probably not even noticeably dimmer. But if you take an oxygen sensor, which maxes out at a volt, and you lose half of that through voltage drop because of corrosion between the sensor and the computer that's measuring it, that sensor is going to be wildly inaccurate. So basically, think of the computer as a voltmeter, and think of the wires between the computer and the sensor as voltmeter leads. The early ones only had a positive voltmeter lead. The later ones, all of them now have both, right? So they'll have a signal wire here, right? But they'll also have a ground wire. Typically, there will be two more wires that operate a heater. So oxygen sensors now are heated oxygen sensors. And what that does is that gets them into operation faster. They do not work when they're cold. So those heater wires, they really have nothing to do with the sensor reading. They're a separate circuit. And the heater can go bad without the sensor going bad, although you will get a code for a bad heater circuit. The reason for the heaters is that these sensors have a tendency to cool down in traffic. So if the engine's idling, there's not very much exhaust flowing over the sensor, it can cool down. Or they wouldn't work when the engine started up cold. So there was a lot of time where the computer did not have the benefit of the information coming out of this sensor. So by putting a heater into it, it gets it working faster, and it keeps it working when things are, when there's not much exhaust flowing over it. Picture you're on a California freeway at rush hour, thousands of cars, bumper to bumper, all idling. And every one of those oxygen sensors stops working because the car is idling. So now they're inaccurate, right? The computers no longer have air fuel information. They're guessing. That contributes to significant pollution. By putting in heated oxygen sensors, now all those thousands of cars are still operating in closed loop. In other words, the computer can still see the sensor. It keeps the sensor working, and that is a significant improvement. All right, I don't care about the heaters right now, though. I just care about the sensor itself. And this may be a little oversimplified, but notice here you've got an air intake opening that can allow outside air into the inside of this thimble. And so air, which is 70%, 78% oxygen, right, is hitting the inside of this thimble, right? So the oxygen molecules in the air are reacting with the coating, the internal plate surface, right? And then exhaust gas is coming in through here. So this section of the sensor is in the exhaust, right? So the exhaust gas is coming in through there, and it's hitting the outside of this sensor thimble, right? This plating, right? And any oxygen molecules in there are reacting with the outside surface of this sensor body. If they are both the same, in other words, if the reactions generate the same number of electrons, right, on the inside and the outside, there's no difference. That is a zero voltage. If, on the other hand, there is a big difference between what's happening on the outside surface and what's happening on the inside surface, the outside and the inside. So if there's a large difference in chemical reaction, then that shows up as a higher voltage, up to about a volt. So this is a little bit of a variable battery. It uses a chemical reaction between the oxygen in either the outside air or the exhaust, and a sensor tip. There's a chemical reaction there as the oxygen hits that, releases electrons. If they both release the same amount of electrons, then they both have the same charge. There is no difference. There is no voltage, right? But if they release different numbers of electrons, now we have voltage. So pretty simple. Again, this sensor, I'm calling it a generator. This does not require an external voltage in order to operate. It creates the voltage, it generates it, somewhere between 0 and 1. And typically, the computer interprets 1 volt as being very rich, 0 volts as being very lean, meaning the exhaust has close to as much oxygen in it as the air does. 0 volts, very lean. Exhaust gas oxygen sensors, and more specifically, heated oxygen sensors have they've been around since late 70s, and they've had one limitation that, well, there's probably more than one limitation, but one I'm thinking of. When an engine is operating at stoichiometry, so this is something we talked about last semester, right? Stoichiometry for gasoline is somewhere around 14.7 to 1. And so if we're at 15 to 1, 16 to 1, we are lean. And if we're at 14, 13, 12 to 1, we're rich. The trouble with an oxygen sensor, a regular oxygen sensor, if you were watching the oxygen sensor voltage and a car was running at stoichiometry, so it would be averaging about a half a volt, right? So this sensor goes from 0 volts to 1 volt. It averages about a half a volt when everything is going correctly. So as long as you're trying to run your engine at stoichiometry, then the computer can watch this sensor. As soon as it sees the voltage start dropping below a half a volt, we're heading into lean territory. Better increase the fuel delivery a little bit, and then watch again, and now we see it start to climb above a half a volt. We're heading into rich territory. Better decrease the fuel delivery a little bit. And this is how this feedback loop has worked for years. The trouble with it is, what if we want to run our vehicle at something other than stoichiometry? So conventional oxygen sensor, we're watching the voltage, we're at 14.7 to 1. Let's say we want to tweak the air fuel mixture and we want to go to 15 to 1. That's not super far off of stoichiometry, right? Our oxygen sensor voltage level is going to start to drop. Let's say we go to 16 to 1, 17 to 1. Now here's the problem. At this point, the oxygen sensor voltage has hit 0. It's putting out nothing because there's not enough of a difference between the exhaust oxygen content and the outside air oxygen content. This sensor has bottomed out. So we're at 17 to 1, let's say, and the sensor's putting out 0 volts. Now what happens? We go 18 to 1. It's still putting out 0 volts. 19 to 1, still putting out 0 volts. How do we have any idea what our air-fuel ratio is? We don't. We just know that it is less than, a certain number. We don't know how much less than that. Here's an analogy, right? Let's say you're driving along and your speedometer only goes up to 80 miles per hour. As long as you're driving less than 80 miles per hour, you know how fast you're going. But once you hit 80 and the speedometer is pegged, now you get to 85, the speedometer is still pegged, right? You get to 90, it's still pegged. 100, you have no idea how fast you're going, right? You're outside of the possible measuring range of that speedometer. The same goes with conventional oxygen sensors, right? As the engine is being driven lean, which is desirable for fuel economy, once we hit a certain lean threshold, then the sensor has hit zero. And after that, we don't know how much leaner we have gotten, right? Are we at 18 to 1? Are we at 19 to 1, 20 to 1, 30 to 1? No idea. Right? So in order to run, and a lot of direct inject cars run leaner than that under certain conditions, right? So in order to have any kind of idea what our air fuel ratio is, once we get to a certain level of leanness, the conventional oxygen sensor no longer does the trick. So uh, let's talk about a different kind of sensor, right? So or you can look at these may be something that show up on a test, right? Let's talk about air fuel ratio sensors. So they're able to measure a much wider range of air fuel ratios. So the computer can operate outside of that narrow band, right around 14.7 to 1. It can operate in a wider band of air fuel ratios and still know what's going on out there. Two basic types, there's the single cell and the dual cell. So I don't want to get into too much detail about exactly how these work, but well, let me warn you that the single cell air fuel ratio sensor looks pretty much exactly like a conventional oxygen sensor. It'll have 4 wires. Um, 2 of them will be the heater, and the other 2 will be the sensor signal and basically the sensor ground. The dual cell, you'll be able to tell it's a dual cell because it'll have 6 wires. If you're measuring the output from the single cell, it will be a varying voltage. So the voltage coming out of it will be based on the air fuel ratio. It will not look like the same types of voltage you have on a conventional oxygen sensor. If you remember, conventional oxygen sensor, I said, has somewhere between 0 and 1 volt. This air fuel ratio sensor, when you're at stoichiometry, you're somewhere in the 3.5 volt area. Right? So don't expect to see the same sorts of things from this sensor, even though it looks the same, the single cell. The dual cell is even stranger to look at because what it counts on is current. It will report current. So this is a little bit weird. The dual cell sensor has an oxygen pump, basically, that attempts to pump oxygen in and out of a chamber to keep, internally, there is basically a single cell sensor, and this oxygen pump is trying to keep that sensor reading stable by pumping oxygen in and out of a chamber. And what you're getting is pumping current measured in milliamps. So for example, let's say you bring up a Ford, late model Ford, very likely to have one of these dual cell sensors. If you bring up air fuel ratio sensor or oxygen sensor, upstream oxygen sensor, you're not going to see volts. You're going to see current in milliamps. And that current can be positive or negative. If you bring up a single cell, you're going to see voltage, but it's going to be different, somewhere in the 3.5 volt range. So what an air fuel ratio sensor does allows the vehicle to be operated at a much leaner ratio, and still the computer can still see where it's at. All right, I think for now, I think the rest of this is best handled in lab. In other words, um, we'll bring in a late model vehicle, and here's what we'll do. We'll look at, let me stop this a minute. So we'll bring one into the shop. We'll bring in maybe a late model GM or something, or a Toyota. It doesn't matter. If it's a 4-cylinder engine, what are we going to have? We're going to have HO2S11, right? Bank 1 sensor 1. And HO2S, of course, is heated oxygen sensor. Right? And we're going to have HO2S12, bank 1 sensor 2. So that's a 4-cylinder. There's only one bank. We're going to have 1-1 and 1-2. If we have a V-style engine, V6, V8, we're going to have 2 banks. So we're going to have sensor 1, bank 1. That'll be HO2S11. Bank 1, sensor 2, so HO2S12, right? And then on the other bank, we'll have a 2-1 and a 2-2. So here's what we want to do. We want to bring this vehicle in. We want to, on the scan tool, we want to monitor the voltage for the upstream, sensor 1, and we want to monitor the voltage for the downstream, which is sensor 2. What we're likely to see on a Toyota or a Chevy or something, single cell sensor looks like a conventional oxygen sensor in front of the catalytic converter, and we will see numbers in the 3.5 volt range. And then the sensor behind the catalytic converter, we can expect to see numbers in the 0 to 1 volt range because it's an old-fashioned oxygen sensor. So that's something we can do in the shop. Then another thing we can do in the shop is we'll bring in a Ford, and we'll use Ford's computer, the IDS, and bring up the oxygen sensors on that, and we can see that that's going to be current in milliamps. On most late model Fords, that's probably what we're going to see. So that's a good exercise for in the shop. And it's important to understand the differences between these and what it is that you're going to see when you look at them. Because if you're expecting 0 to 1 on an old-fashioned conventional oxygen sensor and you plug in and you find milliamps, that's going to be a little bit confusing. So let's just make sure we look at all of those with the scan tool. We've got time. We'll bring in various vehicles and we can do that. So let's talk about one more type of sensor for today, and that's the Hall effect sensor. So this is showing an old distributor, which you're not likely to see these days. But you might see something like this as a cam sensor. And what you're seeing here, you're seeing a magnet, and you're seeing a little chip, right? So here's the magnet, here's the little chip. And let's just try to draw this here, okay? So let's say that this is the magnet, and this is the chip. So magnet, whoops, magnet and chip. Right now, the magnetic field from this magnet is hitting the chip. And a Hall effect, I think I have a video that I'll find that I found on YouTube that explains better exactly what goes on inside a Hall effect. But a Hall effect acts kind of like a switch. So it's going to have a power wire and a ground wire, right? So there's my ground wire. Here's my power wire, right? My negative here. And then the third wire here, this is the output. So unlike the magnetic pickup, the AC signal generator, unlike that, this is fed a battery voltage, or possibly less than battery voltage, but it might be a full 12 volts, right? And it has a ground. So power and ground. Right now, with the magnetic field hitting the chip, essentially it turns it on like a switch. And what comes out here is going to be whatever's being fed in up here. So if that's 12 volts, when the magnetic field hits the chip, we're going to see 12 volts here. If something blocks that magnetic field from hitting the chip, no magnetic field hitting the chip, then this output turns off, and we get nothing out. Right? So we get rid of that. So what could block the magnetic field from hitting the chip? It could be just a hunk of metal that goes in between, and then the magnetic field basically is shunted or is blocked from hitting the chip. The chip turns off. So here's what you're seeing: the shutter blade, right? This is rotating. You can see there's a gap here, and there's a blade here. So as this piece rotates, sometimes, let me get rid of all of this stuff here. Right? I can't seem to get, there we go, okay. So sometimes there is a window or a gap between the magnet and the chip, right? And sometimes there's a blade between, like we're showing right here, between the magnet and the chip, blocking that magnetic field. So as this thing rotates, this chip is going to be turning on and off. So what's going to come out is on, stay on for a little bit, off, stay off for a little bit, on, stay on for a little bit, off. That's what's known as a square wave digital signal, right? So as this rotor rotates, the voltage level coming out of that circuit is going to flip on and off. So what can we use that for? Just like the crankshaft position sensor we saw as a AC signal generator, the computer can count how often or how rapidly, right, the frequency of this signal turning on and off, and it can translate that into some sort of RPM, some sort of rotational speed signal. So what you're looking at here with a Hall effect, you're looking at just another way of doing the same thing that AC signal generator did, only it's just a different technology, right? It's taking a voltage you provide to it, right? So it's not generating anything. You're providing the voltage to it, and it's turning that voltage on and off. And the computer's watching it turn on and off and using that to calculate RPM of something, right? So this could be a crankshaft position sensor. It could be a camshaft position sensor. It could be a wheel speed sensor. It could be an output shaft speed sensor, vehicle speed sensor. The key here, as you might be hearing, is speed sensor, right? Rotational speed. This is one of two ways, essentially, that they measure rotational speed. They either use an AC generator or they use a Hall effect sensor. And the same car might have some Hall effects and some AC generators in different locations on the car. How they decide which to use is kind of a mystery to me. It may have to do with who the vendor is that designs the system for them, right? But these are used very commonly. You'll see them all the time. So if you're trying to decide what you're looking at, when you're looking at an AC generator, right? So we go back to that. The key with the AC generator, right, was we have 2 pins, right? 2 wires going to this thing. Also, none of them will have any, voltage on them, right? Because they are a generator. When we're looking at a Hall effect, so the Hall effect coming out of this, there's going to be three wires, right? There's going to be power, there's going to be ground, and then there's going to be a signal wire. The signal wire will turn on and off as this sensor rotates. So here's an example, right? They're showing a magnet here, the actual Hall chip here, and then this is the rotating shutter wheel that has the windows and the vanes, right? So right now this vane is blocking the magnetic field from hitting the chip. That will turn this chip off, and then when this wheel rotates till one of these windows is between the chip and the magnet, then this chip will turn on. And they have amplifiers and triggers to clean the signal up and make it more of a square wave. So it's a lot easier for the computer to pick up on it. But bottom line, you could stick a voltmeter on this thing and slowly rotate that shutter wheel, and you would see the voltmeter flip up and flip down. And if you spun it fast on DC volts, it would average about half of the input voltage. So if this thing's being fed 12 volts, the meter doesn't react fast enough. It would just kind of average out at 6. All right, I think I want to stop at this point. I don't like to go on for too long, and this is getting to be sort of long, right? So we don't have a lot left. So here's what's going to happen. Next week, I will finish up this set of slides, and then I will post a test, which you will have some time to finish, right? So two things will happen a week from today. I'll post another set or another video, and I will announce that there is a test available for you to take. So in the lab, let's make sure we look at some of this stuff. Typically, you're not bringing in a whole lot of live work, so I'd like to look at these oxygen air fuel ratio sensors specifically. I would like you to see the output from a analog AC signal generator, and I would like you to see the output from a Hall effect. And those are all things we can work on. I have worksheets for those, so we'll do those in the shop. And I'll see you for another video in a week.